Hello dear students, welcome you all. In this lecture, I am going to discuss about the band reject filters, right? It is band reject filters, right? In the previous lecture, we have discussed about the band pass filters, right? Now, this is totally opposite to the band pass filter, right? Band reject filter means this will be a filter which is going to reject a particular band of frequencies, right? As we see in the case of band pass filter, we were allowing a certain band of frequencies, certain range of frequencies to pass through that filter. But here the things will be totally opposite. Here we will reject a particular range of frequencies, band of frequencies. That's why we call it as a band reject filter, right? Now again, we can have two type of band reject filters. One is wideband reject filter and other is a narrow band reject filter, depending upon the frequency response. If I took the frequency response, you can see here, this is the gain, right? You can see here gain versus frequency graph. So here you can see this is gain, this is frequency. So in case of band reject filter, you will get this type of graph, right? So here you can see this particular range, this range of frequencies, right? It is going to be rejected because you see in this region the gain is very low, right? Whereas if we go toward this side, right? If we go toward this side, the gain is stable and it is higher than this gain, right? It is maximum, right? So this is this type of filter that has this type of frequency response is called as a band reject filter, right? Now if this band is quite large, clear, then that is called wide band reject filter. But if this band is very narrow, right, then it means it will be, in that case it will be like this, clear. If this band is very narrow, right, then that in that situation we call the filter as a narrow band reject filter, or it is commonly known as a notch filter, right? It is commonly known as a notch filter. So in this lecture I am going to discuss about the notch filter in details, right? So if I come to the circuit diagram, the notch filter consists of two important parts, right? So one is the filtering unit and the second is a operational amplifier. So I am going the circuit diagram of a filtering unit, right? It will be like right here you will have right. So this is about the circuit diagram. Again here you will have this and this. Yeah. So now I'm going to put the values of various resistances and capacitances in this circuit. So this is resistance, this is again resistance, Both these are resistance R. Clear? Here we have a capacitance, and here it is a ground, virtual ground. Again, here we have virtual ground, right? It is resistance. It is R divided by 2. It is again a capacitor. It is again a capacitor, right? This is C and this is C. It is 2 times C. Clear? This is B output. Clear? And this is V input, right? So this is the filtering unit, right? I can say this is the filtering unit of this band reject filter. Yeah. This is what? Filtering unit. Filtering unit means the circuit in which the actual, the process of band rejection takes place, right? This is one component. The second component is a operational amplifier working in non-inverting mode as a voltage follower. Clear? So it will be, this is op-amp, right? So here right. So this is operational amplifier. Now I'm going to again put the values of different resistors and all other components. So this is here B input. Clear? It is A gain of this basic amplifier. It is positive, it is negative, it is plus B.Cc, it is minus B.E. This is load resistor RL, right? And this is V output. Clear? This is ground, right? So you can see here, what is this? This circuit is basically of a voltage follower. Right? This is a voltage follower, means simply V output is equal to V input. Clear? But our voltage will appear here, the same voltage will appear at the output terminal without any loss, without any attenuation, right? Without any reduce or increase in gain, right? So also it is working in as the non-inverting mode. So it means the sign of the output and input will be same, right? So we will combine these two. So it is clear that we have two different sections in this band reject filter. One is filtering unit and second is voltage follower. So what we will do, we will connect this section with this. I can connect it here. Clear? Simply I will take this, right, take it here and give it to this, right? So now it becomes a notch filter or a narrow band reject filter, right? So this is the simple circuit diagram of this notch filter or narrow band reject filter, right? Now what is the task? Now our task is to simplify this circuit and to find out the value of this voltage, right? don't confuse with this B output and B output. Now I am going to give this as name B output dash. Clear? I can write it as B output dash. Clear? So that this B output is now going to become B input here, and that will give you B output. Simply means this B output is equal to this. Clear? Because it is a voltage follower. Right? Now here you can raise a question that what is the need of this circuit? Right? So as I told you earlier that this voltage follower is going to make the gain of the output coming from here stable. It is going to reduce any unwanted disturbance that is induced in this circuit, because this is the property of the operational amplifier, right? It will also maintain whatever voltage level of the signal will be there, right? Otherwise there can be a decrease in the amplitude amplitude of the signal, right? So this is the use of this operational amplifier here, because this question came in mind, because the same amount of voltage what is appearing here, that is going to appear here. So what is the need of it? So need is that, right? Now I am going to analyze this circuit, right? So whatever voltage I will find out here, B output, that will be simply output, right? To analyze this circuit, what I will do, I will simply again take a simplified approach, in which I will take this circuit, or I can simply even take this case, rather drawing the circuit again. So now I am going to erase this part of the circuit, right? 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 So in that case it will become like, now this is resistance R by 2, because it was on ground, so we can make then both and one ground, right? Now this is 2C, this is CC, and this is V output. This is let node C, this is node A, and this is node B. Clear? If I write the value of the capacitive reactance here, then it will become 1 upon CS or SC. It is again 1 upon CS. It is 1 upon 2CS, right? What are these? What are these values? These are basically the reactance, we can say impedance of these capacitors. Now look at the various current flowing in this circuit. Let I1 current flows toward this side. Clear? Then the current going toward this side is I2, going toward this side is I3, this current going toward this side is I4, then current entering here is I5, right? So same current I3 comes here, it comes here, and then it enters toward this side. So I5 is equal to I4 plus I3. Now we will apply Kirchhoff's junction rule at different junctions, right? So first of all, we will apply it at junction A. So at junction A, you can see clearly that I1 is equal to I2 plus I3, right? So when you take it in terms of voltages, it will become B in minus BA, right, upon R is equal to I2 means BA minus 0, because here it is ground, 0 divided by 1 upon 2CS, right? Plus I3 means BA minus B output upon R. Clear? So now you will simplify it. Clear? So when you will simplify it, you will get the value of VA. Clear? So when you will get the value of BA, it will simply become V in plus B output divided by 2 plus 2 RCS. So when you will simplify this equation, you will get simply this. Clear? I'm not going into these steps. Similarly, we will apply the Kirchhoff's current rule at node B. Clear? Now we are going to apply. So you can see at node V, I5 is equal to I3 plus I4. I told you in the beginning also. So it will become I5 is equal to I3 plus I4. So again the same thing. Clear? I5 means B minus 0 upon R by 2. That is equal to I3 means you can see here B input, not B input, B output minus B upon 1 upon CS. This is I3. This is V output minus VB, right? Plus I4 means B input minus BB upon 1 upon CS. I4 here, V in minus VV upon 1, right? So this is again, this was equation number 1. This is equation number 1, right? This is equation number 2. So again, when you will solve this equation, what you will get? You will get the value of BV. You will solve it for VV, right? So when you will solve it for VV, you will get RCS into B in plus B output divided by 2 plus 2 RCS. Clear? So this is what you get after simplification. Clear? So this is equation number 3. Clear? Now we have BA and BB. Clear? So now applying Kirchhoff's junction rule at junction C. So you can see that at junction C, I3 is equal to I3, right? So I3 is equal to I3. It means BA minus B output upon R is equal to B output minus B upon 1 upon CS. Look at the picture. BA minus B output. BA minus B output upon R, right? This is first term. I3. Now from here, B output minus BV upon 1 upon CS. Clear? So when you will simplify it, it will give you B output is equal to BA plus RSC BB upon 1 plus RCS. Clear? After simplifying this term, you will get this. This is equation number 4. Now it might be clear that what is the next step. The next step is to put the value of BA and VB. It is here, BV is here, BA is here. So when you will put, because you see here clearly from here, if you put the value of BA and VV, you will get an equation in terms of RCS and V input and V output. So when you will put this value and you will rearrange this equation for V output upon B input, I am writing it directly, V output upon V input, right? You will get the value. Let's take the step of putting the value. Then I will write it. Let's consider one step. B output is equal to BA plus B output divided by 2 plus 2 RCS plus RCS into RCS into B input plus B output divided by 2 plus 2 RCS, the whole term divided by 1 plus RCS. You can see here what I did. I put the value of BA, B in plus B output, 2 plus 2 RCS, clear, first term, into RCS multiplied by BV. BV means RCS, B input plus B output divided by 2 plus, right? So what I said, you get the equation here. Now what we will do, we will rearrange this equation and separate it for B output upon B input. You will get 1 plus R square C square S square bracket divided by R square upon C square. Similarly, in the denominator, you will get R square C square S square, right, plus 4 RCS plus 1 divided by whole term divided by R square C square. So it get cancelled and you get this term here. So when you will simplify it, you will get B output upon B input is equal to S square plus 1 upon R square C square divided by S square plus 4S upon RC plus 1 upon R square C square. So what I did after cancelling these, I divide both numerator and denominator by R square C square. So I got this equation. Now this equation can be written as S square plus vega n square divided by S square plus 2 zeta vega n s, right, plus vega n square. Clear? Here vega n is clearly equal to 1 upon RC. So Fn is equal to 1 upon 2 pi RC. This is the notch frequency. Clear? So you see here what is the B output upon B input. This is equal to this function. This is the transform function for this band reject filter, where Fn stands for the minimum frequency, notch frequency. Clear? This is the minimum frequency, notch frequency. Clear? And this will be the, these two values will be there. This is, if I redraw this graph, then you can have it. You will have this type of graph. Clear? Like that. So here it is the, you can have it like this. Right. So you can see all these frequencies. This is Fn, notch frequency. Clear? This is Fl. This is Fh. Clear? So notch frequency is the minimum frequency. Clear? In this frequency, minimum gain, not frequency, but minimum gain. The frequency at which gain is minimum, right? And this is the value. These are the values at which this is what AF, and at this it will be AF divided by under root 2. That is 0.707 AF. Clear? So this is what? This is the output of this circuit. Clear? Sorry,